Welcome to the Before AGI podcast. Today, we are diving deep into a really fascinating area of AI that's becoming more and more crucial, and that's federated learning. For our listeners who are really interested in understanding this whole world of cutting-edge AI, but without getting super bogged down in the technical details, we've gathered a ton of info to unpack this really clever and privacy-preserving approach to AI.
Think of this as your express lane to understanding how AI can become incredibly powerful through collaboration, especially when keeping data private is absolutely essential. We'll explore exactly what federated learning is, why it's such a big deal, and where it's heading, highlighting real-world uses and those trends that anyone interested in the future of tech should be aware of. Our mission today is to give you a crystal clear understanding of federated learning, cutting through all that jargon to reveal the core ideas and why they matter to the future of AI.
So let's unpack this. In the simplest terms, what exactly is federated learning?
At its core, federated learning is a method for multiple different entities. And by entities, we can be talking about large organizations, or even the devices we use every day to train a shared AI model without ever having to pool all the raw data in one place. The game changer here is that we can achieve very powerful collaborative learning while making sure everyone's data stays private and secure.
That sounds like a pretty big shift from how AI training has traditionally been done.
You're absolutely right. The usual way involved collecting all the data in one place, training the AI model on that big centralized data set. Federated learning flips this on its head. It brings the AI model training to where the data already lives, on individual devices or within separate organizations.
And I came across these terms, centralized and decentralized federated learning. What's the key difference for us to grasp?
That difference boils down to how the whole training process is coordinated. With centralized federated learning, you have a central server that's kind of like a conductor in an orchestra. This server sends out the initial AI model, and then it collects all the updates from everyone who's participating in the training. Then it combines those updates to make the overall model better.
So the central server has a pretty big job in that setup.
Exactly. It's often a simpler approach to set up and manage, but it does mean you have a single point of coordination and potentially a single point of failure in the system. Now, decentralized federated learning, that's a different story. There's no central server calling the shots. Instead, the participants, whether it's companies or devices, talk directly to each other. They share their model updates and figure out how to combine them without a central authority.
That decentralized approach sounds a lot more self-reliant. What are the pros and cons to consider there?
The big plus with decentralized federated learning is that it's more robust. There's no single point of failure, so if one participant drops out, the rest can usually keep going. The trade-off is that managing the interactions between everyone becomes more complex since you don't have that central coordinator.
Now, one term that popped up a lot was data heterogeneity. You said it's a key characteristic of federated learning. What does that actually mean for us in a practical sense?
Data heterogeneity basically means that because the data stays local with each participant, the type and amount of information they each hold can be quite different. Imagine hospitals training a model to diagnose a specific disease. One hospital might have lots of data from older patients. Another might have more data from younger patients.
So it's not like everyone has an identical piece of the same puzzle.
Exactly. Everyone's data is unique. Now, this is both a defining feature and a challenge for federated learning. It reflects how data is often distributed in the real world, but it means that federated learning systems have to be smart enough to work effectively, even when everyone's data is different.
Okay, so we've got this distributed training approach where everyone's data can be quite varied. How does the training process actually work in practice?
Let's break down the steps involved in centralized federated learning. It starts with an initial AI model called the global model. This global model is sent out to all the participants or clients. Each client then trains the model using their own local data. It's important to note that the raw, sensitive data never leaves their control. Then each client sends back their updates to the model, not the entire updated model itself, just the changes they made based on their training. These updates are then sent back to the central server, which combines them using a technique called aggregation. This process results in a new, improved global model that has learned from everyone's data without ever directly accessing it. This entire cycle, the distributing of the model, local training, sending back updates, and then aggregation at the server is repeated multiple times, refining the global model with each round.
It's like a continuous learning loop, drawing insights from everyone's data without compromising their privacy. And I also came across different ways the data can be partitioned in federated learning, horizontal and vertical. Can you explain the difference?
Sure. The key difference is how the data sets from the participants overlap. Let's take horizontal federated learning first. Imagine several hospitals, each collecting the same types of health data, like blood pressure, heart rate, age, and so on. They all have the same features or data points, but for different patients. This is horizontal federated learning, where the data sets share common features, but different samples or individuals. It's sometimes called sample-based federated learning.
So it's like having the same columns in a spreadsheet, but different rows for different people.
Exactly. Now, vertical federated learning is different. Imagine two companies that have data on the same set of customers, but each company has different types of information about these customers. One might have financial data, the other social media data. They have different features, but for the same samples. This is vertical federated learning, also known as feature-based federated learning.
In that case, it's like having the same rows in a spreadsheet representing the same people, but different columns containing different types of information about them. When would you use each of these types?
If the data sets have overlapping features but different samples, horizontal federated learning is the way to go.
Yeah.
But if they have overlapping samples but different features, then vertical federated learning makes more sense.
The core promise of federated learning is enhanced privacy. But is sharing just the model updates really enough to guarantee that individual privacy is protected?
Sharing model updates instead of raw data is a huge step towards privacy, but it's not always foolproof on its own. This is why federated learning systems often use additional techniques to further safeguard sensitive information. These are often called privacy-preserving techniques.
Okay, so what are some of those extra techniques? Differential privacy came up a lot in our research. What's the basic idea behind that?
With differential privacy, or DP, the idea is to add a bit of carefully controlled random noise, either to the model updates that each client sends to the server or to the final global model itself. Think of it like adding a little bit of static to a radio transmission, enough to mask individual signals without completely ruining the message.
So how does this added noise protect user data?
This noise makes it statistically very hard to figure out if any single individual's data had a noticeable impact on the final trained model. By obscuring the contribution of any single data point, differential privacy provides a quantifiable guarantee that the model's output isn't overly sensitive to any one person's data.
What about the privacy budget, that term with the Greek letters epsilon and delta?
Right, those are important. Epsilon and delta are like control knobs for differential privacy. They let you adjust how much noise is added, and therefore how much privacy is protected versus how accurate the AI model is. A smaller epsilon means more noise and stronger privacy, but it might make the model a bit less accurate. Delta sets an upper limit on the chances of a privacy breach, even with differential privacy in place.
And then there was this distinction between local and central DP. Where is this noise added in each approach?
With local DP, the noise is added on each device before the model updates are even sent to the central server. So the server never sees the original update from any single client. With central DP, the noise is added by the server after it has all the updates. So the initial updates are sent as is, but the final global model gets the noise added before it's released.
What are the upsides and downsides of each approach?
Local DP offers stronger individual privacy since the noise is added right at the source, on the device itself. However, adding noise to every update, especially with lots of participants, can sometimes hurt the overall accuracy of the final model. Central DP tends to have less impact on the model's accuracy because noise is only added once, but it does mean the server briefly sees the raw updates before adding the noise.
Another technique was secure aggregation. That sounds like some secret code for combining information.
You could say that. Secure aggregation, or SA, uses cryptographic techniques to combine the model updates in a way that the server can't see any individual contributions.
How does that work? It sounds like magic.
The clients encrypt their model updates in a special way, and the server can do math on these encrypted updates without decrypting them. Only the final combined result can be decrypted, and that often requires participation from multiple clients to unlock it.
So the server can learn from the combined updates, but can't peek into anyone's specific contribution. Why is that so important for privacy?
It's crucial because it means that even the central server, the one coordinating everything, never sees the exact changes that any individual client made based on their own data. It drastically reduces the risk of anyone figuring out sensitive information from the updates.
Then there's homomorphic encryption. That sounds super advanced, like something out of a sci-fi film.
It's definitely on the cutting edge. With homomorphic encryption, or HE, you can actually do computations on data that's still encrypted without decrypting it first. Imagine doing math on those locked boxes without needing the key to open them.
How could that be used in federated learning?
In federated learning, HE could be used to completely encrypt the model updates that are sent by the clients. The server would then do the aggregation on these encrypted updates, and only the final result would be decrypted. This would provide very high privacy, since the server would only ever see encrypted information.
That sounds amazing. Are there any downsides to using it?
The main limitation right now is that HE is very computationally intensive. Doing complex math on encrypted data requires a lot of processing power, which can slow down the whole federated learning process. It's a hot research area, though, and as it gets more efficient, we could see it used more widely in the future.
And lastly, there's secure multi-party computation, or SMPC. How does that fit in?
SMPC is a more general set of techniques that allow multiple parties to do computations together while keeping their individual inputs secret. Imagine a group of people calculating the average of their salaries without anyone having to reveal their own salary to the others.
So how can SMPC be used in federated learning?
SMPC can be used for the secure aggregation of model updates. It's like an alternative way to achieve what secure aggregation protocols do. It can also be used for other secure calculations during the federated learning process, like securely evaluating the model's performance or sharing specific parameters.
Are there any disadvantages to using SMPC?
Similar to homomorphic encryption, SMPC can be quite complex to implement, and it can be demanding on computing resources. This can make the whole federated learning process take longer. The complexity depends on what you're trying to calculate and how many participants are involved.
So we see that federated learning's main attraction is privacy, and it often uses these other clever techniques to really make sure that privacy is protected. But beyond just privacy, what other advantages does federated learning offer?
You're right, it's not just about privacy. It has a bunch of other great benefits too. We've already talked about enhanced privacy and security, but it's worth repeating that federated learning keeps the raw, sensitive data spread out and local, which reduces the chances of large-scale data breaches.
A huge advantage in today's world where data is so valuable. What else does it offer?
It also promotes something we call data decentralization and democratization. It lets different organizations or entities collaborate and share knowledge, even if they can't or don't want to directly share their raw, private data. This unlocks a lot of possibilities for innovation and for finding valuable insights from data sets that were previously inaccessible.
That potential to speed up progress in all sorts of fields sounds really exciting.
It is. And since models trained with federated learning often learn from a much more diverse collection of data, they can often be more generalizable and robust. They perform better on unseen data and are less susceptible to biases that you might get when training on just one data set. It's like giving the AI a more well-rounded education.
Makes sense. A more diverse training process means a more adaptable and reliable AI model.
Exactly. And there's another benefit, which is reduced communication overhead. Because it mostly involves sending model updates, which are much smaller than entire data sets, federated learning saves a lot of bandwidth and network resources. This is especially important when you have lots of participants or unreliable internet connections.
Especially important for things like smartphones and those Internet of Things devices.
Right. And the way federated learning is set up makes it very scalable and efficient. The workload of training the model is spread out across many devices, so you can handle much larger data sets and potentially train models faster than if you were just using one central machine.
So more privacy and improved efficiency, it sounds like a win-win.
Exactly. And then there's the matter of regulatory compliance. In heavily regulated industries like healthcare and finance, where there are strict rules about data privacy, federated learning provides a way for organizations to collaborate and advance their AI without breaking those rules. The sensitive data never leaves their control. This is a game changer for using AI in areas where data privacy is a major concern.
It opens doors for innovation in areas that were previously very difficult to navigate because of those privacy concerns. Now, let's move on to real-world applications. Where are we seeing federated learning being used today?
We're seeing it pop up in all sorts of areas. In healthcare, for example, hospitals could use federated learning to train an AI model to diagnose a rare disease without having to directly share their sensitive patient data. There are already companies like Oken using it for cancer detection, and it's being explored for predicting the severity of infectious diseases like COVID-19.
That's a great example of how federated learning can be used in a field where data privacy is paramount. What about finance?
In finance, banks and other institutions are looking at how federated learning can help them collaborate on things like fraud detection or credit risk assessment without having to share their customers' sensitive financial data. This is especially important because of the strict regulations in the financial industry. We're already seeing investigations into using federated learning for anti-money laundering efforts, where institutions can work together without exposing their customer data.
It makes perfect sense for those highly regulated and competitive industries where data confidentiality is so important. And are there applications outside of those more regulated sectors?
Absolutely. The Internet of Things, or IoT, is a really promising area for federated learning. Think about the keyboard on your smartphone. It learns your typing patterns and preferences to give you better predictions, and it does this using federated learning. It processes your typing data locally on your device and only shares anonymized updates without sending everything you type to the cloud. In industrial settings, federated learning can be used to predict when machines might fail, using sensor data from individual machines without having to share all that data centrally.
So it's not just about big organizations collaborating, it's also about improving the devices we use every day while keeping our data private.
Exactly.
Federated learning sounds amazing, but you mentioned earlier that it's not a perfect solution. What are some of the limitations and challenges that still need to be addressed?
You're right, it's not a silver bullet. There are definitely challenges that researchers are working on. One is communication overhead. Even though federated learning sends much less data than traditional methods, if you have a ton of participants or bad internet connections, sending all those model updates can still slow things down.
So even though it's better than sending huge data sets back and forth, there's still quite a bit of communication involved. How can we reduce that overhead?
Researchers are exploring different techniques. One is model compression, which basically shrinks the size of the updates being sent. Another is client selection, where only a select group of participants are involved in each training round.
Another challenge mentioned was system heterogeneity. What does that mean?
System heterogeneity means that the devices or organizations participating in federated learning can have very different capabilities. Some might have powerful processors and fast internet, while others might have limited resources. This difference in performance can make things tricky, as the slowest participant can hold everyone else back.
So how do you deal with those differences in capabilities?
There are a few approaches. One is to use adaptive learning rates, where the learning process is adjusted based on how fast each client can learn. Another is personalized federated learning, which tries to create custom models for each user, taking into account the unique characteristics of their device.
And you also talked about statistical heterogeneity, with the data being non-IID. Why is that a big problem for federated learning?
Statistical heterogeneity means that the data from different participants is not equally representative of the overall population. This is a challenge because the global model might end up being biased towards certain types of data, depending on which participants had the most influence during training.
So the model might be super accurate for some users, but not so much for others because of those imbalances in the data.
That's right. To tackle this, researchers are looking at things like personalized federated learning, where they try to create more customized models for each client, and multitask learning, where the model learns multiple related tasks to make better use of the diverse data.
Even though federated learning is all about privacy, are there still security risks to worry about?
Unfortunately, yes. Federated learning is not completely immune to attacks. One example is model poisoning, where someone tries to sabotage the global model by sending bad updates. Another is gradient inversion, where someone tries to figure out sensitive data by analyzing the model updates.
Those sound pretty serious. What can be done to protect against those attacks?
There are a few lines of defense. Secure aggregation protocols stop the server from seeing individual updates. Differential privacy adds noise to the updates, making it harder to extract information. And techniques like client authentication and anomaly detection can help spot and block bad actors.
It sounds like making sure the global model learns effectively and is fair to everyone is a big challenge in this setting.
You're right. It's difficult to guarantee that the final global model works well for everyone and doesn't unfairly favor certain groups. Techniques like weighted averaging of the updates and special algorithms designed for non-IID data are being developed to address these issues.
And just the task of setting up and managing these federated learning systems at a large scale seems like a big undertaking.
Definitely. When you have potentially millions of devices or many different organizations involved, things can get complicated. It requires a strong infrastructure and efficient ways to manage the entire training process.
And what about the fact that the quality of data and how it's labeled might be different across all these participants?
That's an important point. If the data from different participants varies in quality or how it's labeled, it can definitely mess up the training process and make the final model less accurate. Making sure there's some level of consistency and quality control across all the data sources is a challenge that needs to be addressed.
So lots of challenges to overcome, but the potential benefits of federated learning seem to outweigh the difficulties. Can you remind us about the main architectural approaches? We talked about centralized versus decentralized earlier.
Sure, the choice between centralized and decentralized depends on what you're trying to do and what your limitations are. Centralized is usually easier to set up, but requires a reliable central server. Decentralized is more robust and gives participants more independence, but it's more complex to coordinate.
And are there any tools or frameworks that make it easier to build these federated learning systems?
Yes, there are several open-source frameworks that can help. TensorFlow Federated, or TFF, is a popular choice, developed by Google. PySift, which is built on PyTorch, focuses on privacy-preserving machine learning. Flower is very flexible and can be used with different machine learning libraries. And NVFlare from NVIDIA is designed to handle large-scale federated learning.
So developers don't have to start from scratch. What should someone consider when choosing a framework?
Some factors to consider are how many devices or organizations will be participating, how sensitive the data is, how reliable the internet connection is, and how much computing power the devices have. Different frameworks are better suited for different situations.
You mentioned personalized federated learning, or PFL, as a promising direction. Could you expand on that a bit?
The idea behind PFL is to go beyond just training a single global model. Instead, it tries to create custom models for each user, recognizing that a single model might not work best for everyone. It's like having the benefits of collaborative learning, but with personalized results.
So it's like combining the power of collective intelligence with individual tailoring.
Exactly. And researchers are constantly improving the privacy-preserving techniques used in federated learning, developing stronger versions of differential privacy, more efficient, secure aggregation methods, and even hybrid approaches that combine different techniques. This is crucial for keeping up with evolving privacy concerns and regulations.
What about the role of blockchain in federated learning? That seems like it could be a good fit.
There's definitely potential for blockchain to improve the security, transparency, and accountability of federated learning. Its decentralized and immutable nature could provide a tamper-proof record of everything that happens, which could increase trust and make it easier to track who contributed what. We're also likely to see more hybrid approaches, where different types of federated learning are combined to take advantage of their strengths.
And finally, as these systems get bigger, what about energy efficiency? Especially for devices that rely on batteries. And what about auto-FL? What does that mean?
Energy efficiency is definitely a concern as federated learning grows and evolves more and more devices, especially for things like smartphones and IoT sensors. Researchers are looking for ways to optimize the training process to reduce energy consumption. And AutoFL, or automated federated learning, is about using automation to make the whole federated learning process easier and more efficient. This includes things like automatically selecting the best model architecture and fine-tuning the system's settings.
So, to wrap things up, how does federated learning compare to other privacy-preserving AI techniques like homomorphic encryption and secure multi-party computation? What are the trade-offs?
All of them aim to protect data privacy while allowing AI development, but they go about it in different ways. Homomorphic encryption offers very strong privacy, but can be computationally expensive, making it less practical for large-scale applications. Secure multi-party computation also provides strong security, but can be resource-intensive, especially with many participants. Federated learning tends to be more balanced in terms of privacy, efficiency, and scalability. It focuses on keeping data local and uses secure aggregation and differential privacy to protect shared updates.
So the best approach depends on what you're trying to achieve and what resources you have. When is federated learning the best choice?
Federated learning shines when you have a lot of data spread across many devices or organizations, when you need efficient training, and when strong privacy guarantees are essential.
Well, it's clear that federated learning is a really important and exciting development in AI. It provides a powerful way to build intelligent systems collaboratively while respecting data privacy.
And its applications are vast, ranging from groundbreaking healthcare research to improving the devices we use every day.
There are challenges to overcome, but the research and development in this field are really promising.
We've only scratched the surface of federated learning, and it's definitely a technology to watch as AI continues to evolve.
If you want to learn more about AI and stay up to date with the latest trends, be sure to subscribe to the Before AGI podcast for more discussions like this one.
And if you're interested in the more technical side of AI, including federated learning, you can check out my YouTube channel, Ian Ocheng, Ochieng AI, where I share tutorials and insights.
What are your thoughts on federated learning? What questions do you have? We'd love to hear from you, and maybe we can explore your questions in future episodes. Thanks for joining us as we explored the world of federated learning.